Can you hear me? Okay. All right, can you hear me? Thank you. So I'd like to thank the organizers for the invitation to come here once again. My name is Rodrigo Capaz. I'm from the Federal University of Rio. And I chose a very broad overview of the things we are doing in our group for the last 1 or 2 years, because this is the first day of the conference, and then I'll take advantage of showing you a large number of different works so we can perhaps establish collaborations later in the week. Okay, let me first introduce our research group at the Federal University of Rio. This is the campus of UFRJ. We have, we call ourselves NAMOR, Nanoscience Modeling in Rio. We have 3 faculty, 2 graduate students, 2 postdocs, and 2 undergraduate students. The systems we study are basically mostly semiconductor systems, mostly also quantum information with semiconductor qubits. This is actually Belita's main research interests. Also, I do a lot of carbon nanostructures and 2D materials, and also some calculations on OLEDs and surface physics. We interact a lot with experimentalists. And we explore different properties: electronic, structural, mechanical, optical, thermal, and magnetic properties. And the tools we use are mostly first principles calculations based on DFT, semi-empirical calculations, mostly tight binding, and most of the results I'm going to show you today are actually using tight binding. And we do a little bit of molecular dynamics simulations also, but also in collaboration with other groups. All right, so this is an outline of this talk. The first part of my talk, I will tell you about some recent work we did on twisted graphene systems. I'll take advantage of the nice introduction that Eric gave us this morning, so I don't have to spend much time on introducing this subject to you. So I'm going to talk about the optical properties of twisted multilayer graphene. I will go into a little bit more detail about the double bilayer graphene near the magic angle and the effects of vacancies in the electronic structure of twisted bilayer graphene. Then I will discuss about impurity state, shallow donors and acceptors in hexagonal boron nitride. I'll talk about recent work we did on the energy barrier for collapse of carbon nanotubes. And in the end, if I have time, I will explore, I will just flash some slides of other works we did in 2D materials, just one work per slide. As I said, just to maximize the chance for interaction with you guys. So again, thanks for Eric. I don't have to take much time on this. This is a slide about twistronics. Twisting graphene is another pathway to explore its very interesting properties. When you twist one layer of, the most common system is actually twisted bilayer graphene. When you twist one layer with respect to the other with a certain twisting angle, you can see that in reciprocal space as displacing the 2 direct cones. And when you displace the 2 direct cones, when they touch here, they actually anti-cross, and then you create 2 Van Hove singularities, log-type Van Hove singularities in the valence and conduction bands. And then you can use that, because since the energy difference between these 2 Van Hove singularities depend on the twisting angle, this is a way to tune the properties of the optical properties of graphene. I think this is running out, the battery. you can tune the optical properties of graphene just by tuning the twist angle. Oh, it came back. All right. And this has been seen experimentally in STM. Thank you. And if you map the Van Hoff singularity separation with respect to the rotation angle, is quasi-linear, but it goes to 0 before 0 degrees in a sense. And this is a signature of the so-called magic angle. Actually, this is running out. The magic angle is an angle in which basically the system developed flat bands, and it's not a semiconductor. Sorry, you don't have Van Hoff singularities anymore, and then you develop some flat bands at the Fermi level. Thank you. Let me go back. And oops. All right. And as Eric told us, this can have very interesting properties. At the magic angle, the flat bands develop, and also related to that, you have the localization of electronic states in the AA regions of the Moore pattern, and all sorts of many bi-correlated effects arise, and this has been seen experimentally last year by the MIT group of Pablo, Rodrigo, and they observed superconductivity, for instance. So this has been discussed. Also the region of a large rotation, large twisting angles is also interesting. For instance, this is also another very interesting work of last year in Science. When you set the rotation angle to be exactly 30 degrees, you don't have a periodic structure anymore, but rather a quasi-crystal, quasi-periodic structure, which also has very interesting electronic properties. So this is a very rich system, but a lot of work has been done already on the bilayer system, and in this work we wanted to explore multi-layer, more than 2-layer structures. So we did calculations of electronic and optical properties of the bilayer, to compare with previous results. This is the notation we use. 1 + 1 means one layer and one rotated layer, or A theta. 2 + 1 is AB stack, is the tri-layer, AB stacked layers, and there's this nice color code as well. So, and one rotated. The 3 + 1 4-layer system, and the 2 + 2 4-layer systems. So 3 ABA Bernal stacking and one rotated, and 2 AB, the two bilayers rotated with respect to each other. So we calculated this, and one expects to have different electronic properties just because of the different dispersions that, for instance, if you compare the 1 by 1, the bilayer, with the 2 by 2, what we call also the twisted double bilayer system. So one has linear dispersion, the other one has parabolic dispersion, and just because of that, one should expect to have slightly different electronic and optical properties, as I'm going to show. So we use a multiple neighbor tight binding method, as Eric also explained, that our hoppings depend on both on distance and the angle, and we actually have a multiple neighbor. That means we have more than second and third nearest neighbor interactions. So it's a exponential. It's a hopping that actually decays exponentially with the distance. So first, let me show you the density of states. This is the density of states of the bilayer. This is of course, it's actually already known from the calculations of the group of Cochino. As you can see, these Van Hoff singularities, both in the valence and in the conduction band, they track nicely with the rotation angle. We can follow this color code based on the variations of the fluminense flag. So you can see that this is the bilayer, the tri-layer, and the 2 4-layer structures. And you can see that the same thing happens for the tri-layers and the 4-layer structures. You also see Van Hoff singularities that depend on the angle. And we actually explore in the band structures actually where exactly in the band structure these Van Hove singularities correspond to. We also look at the optical absorption spectrum. Again, this is the bilayer. This is already known. And these are the results for the tri-layer and the 2 4-layer structures. Again, as the two main take-home messages here are that the number, well, there are also optical features that track with the rotation angle, the twist angle. And the number of, for instance, for the tri-layer, you have 2 peaks, and for the 4-layer structures, you have 3 peaks that change with rotation angle. So the number of angle-dependent peaks is actually equal to the number of layers minus 1. But whenever you have A-B stacking, whenever you have a bilayer system with A-B stacking, you also have a peak in the infrared around 0.3 eV that does not change. You can also have it here and here, and this does not change with the twisting angle. And actually, this comes from transitions from like the top, this transition here, from the top valence band to the second conduction band. And those do not depend much on the angle. So this is a way to actually optically detect in a multi-layer system if you have, well, first of all, the number of layers in your system, and also if you have A-B stacked bilayers. If you plot the energy of those transitions with respect to the twist angle for all systems, the bilayer and the 4-layer and the 3-layer, and you can see that these also they follow some curves that they're monotonic, and again, when the energy goes to 0, it corresponds to an angle, which is an approximation, at least, of the magic angle, and you can see that the magic angles should be different for the different multi-layer systems. In fact, we can see that the magic angles should be slightly larger for the tri-layer and the 4-layer system in comparison with the bilayer structure. Okay. All right. So in an ongoing work now, this is in collaboration with Eric and Leonor Chico. We are now exploring in more detail the flat bands and gaps in the twisted double bilayer systems. Is the 2x2 system, and now very near or at the magic angle. So this is a work that we're just finishing right now. This is also in collaboration with Francisco, who is my postdoc at UFRJ, and I think Francisco has shown this also. I mean, this is for the two twisted double bilayer system. We don't have direct cones, but we have massive bands for the 2 bilayers. And when you rotate them, again, they should anti-cross. And people have been studying this system both experimentally, and Philip Kim and Pablo groups, their very recent work, and also theoretically. And they observe also superconductivity and the emergence of correlated insulating states in this system as well. And the magic angle is, again, slightly larger than in the case of the bilayer. So we did calculations in the system. Once again, we use a tight binding model, as I have shown you before, and we also did, Eric did some DFT calculations using the quantum espresso code. And these are the DFT results corresponding to 2 different rotation angles, 21.8 and 13.1. This blue bands here are the DFT results. One can see, well, in DFT you cannot go to very small angles because the unit cell would be prohibitive. But we see that there is a tiny gap. So the two parabolic bands do not touch anymore. And there is a tiny gap that opens in the system, which is 40 millieV. 40 millieV for 21 degrees and 20 millieV for 13 degrees. And we can reproduce this reasonably well with the tight binding calculations. But when you do a simple tight binding calculation, just as we did for the bilayer, for instance, we have a gap of 6 millieV only. So if we want to reproduce the DFT gap, one actually has to take into account the fact that in this system, the inner layers are inequivalent to the outer layers. So it's a surface type of effect. So one has to add an on-site term to the tight binding Hamiltonian, which is higher for the outer layers and with respect to the inner layers by 20 millieV. So when you do this, then you can actually reproduce the DFT gap. And this again, and by doing that, we can, again, using tight binding, you can do very large systems and go to the magic angle. So these are the band structures for 3.9, 2.3, 1.6, and you can see if you can track the energy gap, the gap at gamma. So this is running out too, but that's okay. Okay, the gap at the K point never closes, but the system eventually becomes metallic because it becomes an indirect gap system. So, and this is the energy. Sorry, this is the energy gap as a function of angle, and it becomes metallic roughly at 1.5 degrees, and the flat bands emerge in a certain energy range, range of angles between 1.1 and 1.3 degrees. So we have a very detailed characterization, the electronic structure of this twisted double bilayer system that recently became very important. So one thing that we wanted to do is to explain why there's always a gap at the K point, and this can be understood by simple symmetry arguments. When you have the bilayer, you have a degeneracy at the Fermi level. This is because of a sublattice and layers symmetry. When you have symmetry operations that take one layer to the other, one atoms in one layer to the other, and this symmetry, it can be broken by, for instance, an electric field perpendicular to the layers, right? So this is well known for a long time. If you apply an electric field perpendicular to the layers, you open a gap because you remove this symmetry. Now let's consider that now approaching two bilayers like this next to each other in a rotated manner, but we approach them, and in this limit, the interactions between the two bilayer systems is small. So, but as soon as they start to interact, because of the twisting, and you can work out the group theory for that. You don't have this symmetry. I mean, the symmetry that you have does not allow you to have a four-fold degeneracy here. So you had two bilayers. You simple-mindedly you would expect now that you have instead of a two-fold degeneracy, a four-fold degeneracy. But group theory prevents you of having a four-fold degeneracy in this, and so the gap, there's a level repulsion that causes the gap to open. So in the end, you have basically, as I have here in this picture. Sorry. Let's see. Each one of these bands is two-fold degenerate, and so the gap must open because of that. All right. one can also look at in the flat band regime the localization of electrons and holes, and this is somewhat similar to the bilayer case. Both electrons and holes, they localized in the inner layers at the AA regions. So it is, and there's some localization in the outer layers at regions which are intermediate between AA and AB. Okay, so this is for the two twisted double bilayer system. Now I'm going to discuss on the effects of vacancies on the electronic and optical properties of twisted bilayer graphene. Again, this is a work with Francisco Kulchak. We wanted to explore if the electronic structure of the bilayer system with this nice Van Hoff singularities that change with the twisting angle, if this is preserved when you introduce defects in your system, for instance, when you introduce vacancies. If you have a single layer of graphene, not bilayer yet, if you have a single layer of graphene and you introduce vacancies, you develop densities of states near the Fermi level. Actually, this is when the only considering a first nearest neighbor in your tight binding Hamiltonian. Once you add second nearest neighbors, you break electron hole symmetry, and actually this peaks becomes broader, actually moves in the direction of the valence band to lower energies, right? Slightly away from the direct cone, like 0.1, 0.2 EV away from the direct cone. And if you increase, T prime is the second nearest neighbor hopping. If you increase the hopping, then the peaks becomes broader and again move to lower energies. This is going to be important. So this has impact in the optical properties. This has been explored by Katz-Nelson group in 2001. This is this is just first nearest neighbor Hamiltonian. If you have localized states here, you can also have, besides the usual Van Hoff singularity that you have from optical transitions between those two peaks, you can also develop some transitions between the localized and extended Van Hoff singularities here at roughly half the energy of this main peak. So this is all single layer graphene. So you wanted to see what happens when you have twisted double layer graphene. And I'm showing you again the results for twisted bilayer graphene without vacancies, just to remind you that we have these Van Hoff singularities that depend on the angle, and that is related to these optical peaks that relate on the angle. And let's see what happens now when you introduce vacancies in your system. So these are the density of states of a bilayer graphene with vacancies. Similarly to the case of monolayer graphene, you develop some peaks in the density of states here, slightly below the Dirac point. And these do not depend much on the angle. And what you're seeing here in black is the twisted bilayer graphene without vacancies, and the red is the density of states of the twisted bilayer graphene with vacancies, 20 realizations of this order. Okay, so but you can see that the Van Hoff singularities are somewhat preserved for large rotation angles. But the interesting thing is when you reach angles in which the Van Hoff singularities in the valence band overlap with the density of states associated to the localized states of vacancies, it washes out the Van Hoff singularity of the bilayer. And this has consequences. in the optical properties. If you look at the optical absorption spectrum, again, what you see is that even for very small concentrations of vacancies, like 0.5%, for large angles, the peaks, the optical peaks, are preserved. But when you go for low angles, basically they are washed away. And this happens again because of the overlap between the density of states of localized states and the density of states of pristine graphene that happens. This overlap happens for low angles. So the main conclusion here is that these absorption peaks, which is a signature for the twisting bilayer system, are not very robust for low angles in the presence of a vacancy type of defects. And this is an important message for people that perhaps use optical characterization techniques to study those systems. All right, so now I'm going to move away from graphene and discuss recent work we did on hexagonal boron nitride. And this is also related to defects and impurities in boron nitride. This is a collaboration with Marcos, also in the Federal University of Rio, and Saif and Fernando Sato at the Federal University of Juiz de Fora. Okay, sorry. I don't Nuno already introduced boron nitride to you. I don't have to explain boron nitride. This is a 2D material that has applications as an insulator in this in this field of nanoelectronics. It has a very large band gap, and it can be used as to encapsulate graphene and other 2D materials, for instance. So we were interested in, since it is a semiconductor, it's interesting to study how you can dope it. So we are looking for different ways of doping boron nitride with donor and acceptor impurities. And but before that, let me just remind you basic concepts related to the shallow impurities in regular 3D semiconductor like silicon, for instance. Because what's important about boron nitride, and that's going to be it's also the case for silicon, that it is a multi-valley system. So in boron nitride, you have the K and K prime. You have two valleys. In silicon is more complicated. You actually have 6 valleys in the conduction band. So in the conduction band, the minimum of the conduction band in silicon is between the gamma and the X point. So you have 6 valleys. So when you dope it, for instance, with a donor, with a phosphorus atom, what happens is that in principle, one would have 6 degenerate ground states corresponding to the 6 valleys. But again, because of group theory, it cannot have a 6-fold degenerate level. So this crystal field splitting breaks this degeneracy. In the end, you have one non-degenerate ground states and other types of degeneracy in excited states. So our idea was to see how that happens in a 2D material, because in 2D material, one expects that those impurity levels are not so shallow, because you have much less screening than what you have in a 3D system. This picture was made for exciton, but the physics of the exciton is very much similar to the physics of a donor or acceptor impurity. It's just a Coulomb interaction between electron and hole in the case of exciton, or between an impurity and one extra carrier in the case of a donor or acceptor impurity. So in a 2D or low-dimensional system, the screening is much less effective. So this is pictorially shown here. you can see that you have a positive and a negative charge. In 3D, all the field lines, they cross the material, but in a low-dimensional system like carbon nanotube or 2D material, most of the field lines, they cross the vacuum region, and this is a way to see how you have much less screenings, therefore you have a much larger Coulomb interaction between the impurity and the electron, and then you expect much deeper levels, right? So so let's see what happens when you have boron nitride. Again, as I said, boron nitride, you have two valleys. We did both DFT calculations and tight binding calculations, and we also did effective mass type of calculations for this system. I'm not going to go into the details of these, so just skip that. I think the graphics are heavy. Sometimes it takes longer. Or maybe the... Oh, there you go. So let me first discuss the case of acceptor impurities. The case of donors are actually going to be very similar, right? So let me discuss the acceptor case. What is going to be important here is that there are two kinds of acceptor states. You can substitute one carbon atom for nitrogen, so one group 4 atom in a group 5 site. And you can also substitute one beryllium atom into a boron atom. Again, this is like group 2 into group 3, and this is group 4 into group 5. And what happens in this case is actually we see a very different level structure. In the case of carbon in nitrogen, and these are the bands, this is the density of states, this is DFT, and this is tight binding. You can already see that the tight binding reproduces quite well the DFT results. So let me focus on the DFT results only. And you can see that in one case, carbon substituting nitrogen, you have basically one single donor state. So this is the top of the valence band. This is one single, sorry, not donor, acceptor. This is the top of the valence band, and this is a single acceptor level, right? And this is already weird because we had two valleys to start with, so there's at least one state missing somewhere. And the case of beryllium substituting boron is even more strange. Instead of two, we have now have three states. You have one doubly degenerate state, which is the ground state. Remember that the whole state's low energy is upper in energy. And you have one whole excited state, non-degenerate, which is non-degenerate, right? So that's why we call these exotic impurity states. This is the title of our paper. Because this is, for instance, is very different from what one would expect from a hydrogen atom picture, and it's also very different from what one would expect from simple valley physics. So you have two valleys, states should come in pairs, right? Okay, so this you can see that tight binding reproduces the DFT results, which is nice. One can look at the wave functions. Let's see, this is the case of carbon on nitrogen. This is the non-degenerate states. You can see that it's quite well localized into the impurity. And these are the two. This is the other case, beryllium on boron, and this is the non-degenerate states. And this is the sum of the two doubly degenerate states. This is DFT, and this is tight binding. The agreement is also very nice between the two. And what you can already see here is the following. The top of the valence band in boron nitride is on the nitrogen site, on the nitrogen atoms. So acceptor states, the wave function is constructed from linear combinations of valence bands that are mostly localized in the nitrogen. Okay, so when you substitute an impurity in the nitrogen site, and since the bulk wave functions already have a large amplitude in that site, this is very different from this case. In this case, you can see there's a node in the wave function here, because you're substituting the impurity for boron atom, and the top of the valence band, there's very little component in the boron side. So basically, in short, this is the reason why you have a lot of difference here between the two cases. In this case, the wave function is localized in the impurity, so the valley splitting is much larger. So that's why you see just one impurity state, because the other states actually dip into the valence band. The valley splitting is large, you have just one state in the gap. Right? But in this case, the ground state is doubly degenerate because the valley splitting is very small. It's almost zero, because the wave function of the bulk has no amplitude at the impurity side, and that's why you have very different level structures in this case. Okay, so that basically explains the difference between the two cases. I think this is because of the battery. Okay, this works. The donor states, they are very similar. I'm not going into that. I don't think I also have time to discuss we developed a multi-valley effective mass formalism, and reproduces most of the results. It reproduces this large valley splitting, and for the case of carbon, this one, and reproduces this doubly degenerate level, but it does not reproduce this this non-degenerate state that you see both in DFT and tight binding. There are some limitations of the effective mass. I can discuss that in more detail if we are curious about that. All right, let me jump and let me discuss the energy barrier for carbon nanotube collapse. Since this is a 2D material conference, I was a bit uneasy about showing a carbon nanotube results, so I decided to call carbon nanotube a graphene nanocylinder. So I'm within the scope of the conference. So what happens here is when you have a very large diameter carbon nanotube, the ground state is not cylindrical anymore, but it's a collapsed structure. And that happens because of the attractive van der Waals interactions between the opposite walls of the tube. It compensates the high curvature that you have to achieve to collapse a carbon nanotube. So this structure actually wins once you have a carbon nanotube for diameters that are larger than 4 nanometers. So the cylindrical structure is actually metastable. So, and this has been known for a while, but no one has ever calculated the energy barrier for going from this metastable configuration to this ground state. And this is what we intended to do. This has been seen experimentally. This is quite interesting. People have done electron diffraction experiments, several nanotubes in a surface, and they have seen that for diameters smaller than like 5 nanometers, this is slightly larger than the prediction from theory. For 5 nanometers, they see basically rounded or cylindrical carbon nanotubes. And for diameters larger than 5 nanometers, they see mostly collapsed single-wall nanotubes. But pay attention to these two cases here. For instance, this one and this one is like 7 nanotube, very large diameter carbon nanotube that stays cylindrical for some reason. So I'm going to come back to this point. So people have explored different ways to try to calculate the energy barrier for collapse. But actually, what most people did was to explore a pathway for collapse which corresponds to a uniform collapse of the carbon nanotube, as if the whole carbon nanotube would collapse simultaneously. And when people do that, they can actually measure not the true energy barrier, but actually an energy barrier per unit length, right? If you take an infinite carbon nanotube, this would correspond to an infinite barrier, energy barrier, and this is, we believe it's unphysical. There should be a finite energy barrier for collapsing a carbon nanotube. But using this uniform collapse assumption, people measured energy barriers roughly of 0.3 eV per angstroms, roughly. It depends on diameter, but this is the ballpark number. So we thought that this would be, again, unphysical, and we were trying to find the true energy, the true minimum energy pathway for collapsing carbon nanotube. So this is, okay, this is, I already said, energy barrier for infinite carbon nanotube would be infinite. And we thought of this collapse as proceeding in the following manner. A local collapse, that initially the collapse would happen locally, and as soon as this nucleation region would be large enough, then it will propagate spontaneously throughout the tube, right? So first of all, we performed constraint minimization simulations for this collapse using classical methods, Lamps code. And what we did, we approached two atoms next to each other, and then we relaxed the whole carbon nanotube, given the constraint that the distance between those two atoms is fixed at certain numbers. So when you do that, the potential energy increases until you reach the so-called saddle point, and then after the saddle point, which corresponds to this situation, the nanotube collapses spontaneously. So this would be the true energy barrier for collapse, and in this case, you already see it seems quite big. It seems like 20 eV. This is kind of strange, and that's the first thing I told my student. But anyway, this is the picture, the movie for this collapse. So as soon as they touch each other, then they collapse spontaneously. So one has to study that for different sizes of unit cell. You have periodic boundary conditions along the length of the tube. So one has to converge it quite well with respect to the length of the tube, but this eventually converges, and then you can have an energy barrier in the limit of an infinitely large carbon nanotube, and that's the number I have here. The energy barrier for an infinitely large carbon nanotube as a function of diameter. And look at those numbers, like 60, 90, close to 100 eV. These are not numbers that we are used to in condensed matter physics. So again, I told my student that it's probably wrong, that it's not very well converged, and I asked him to redo the calculation several times. By the way, he started this calculations when he was an undergraduate student. Now he's in his PhD, but don't worry, he did other things in between. So he did a master thesis in a different project. Okay, so we wanted to understand why that happens. It's consistent with the results we have for the uniform collapse. So this is a picture of the saddle point. So in the saddle point, there is the point of maximum energy along the barrier, along the pathway. One can see that the deformation of the carbon nanotube is very large, it's very extended. It extends around 200 angstroms or so. So if you take an estimate then of the energy of this configuration simply by the number that we had before for the uniform collapse case, which is roughly 0.3 eV per angstrom, times the size of this deformation, which is like huge, 200 angstroms, then you reach a number of 60 eV. So this is consistent. I mean, the number that we get from the static minimizations is at least consistent with this argument, which is roughly the same as the uniform collapse barrier per unit length times the length of the deformation. But we wanted to do more. We wanted to confirm this result further, because this was strange. But I mean, if this is right, then it's interesting, because a cylindrical carbon nanotube would stay cylindrical forever. Once It is born in a cylindrical shape. It will stay cylindrical, at least because for thermal fluctuations, we will never collapse because it would take longer than the age of the universe to collapse, right? So we confirm that using molecular dynamics simulations in collaboration with Alexandre. So these are some molecular dynamics simulations, and what we are trying to do here is to compare. Let me go back a little bit. I want to compare the barrier that one gets from molecular dynamics simulations with the static barrier. But the static barrier, as I have shown before, it depends on the length of the tube. We cannot do very long simulations for very long tubes, but we can actually sit here with very short unit cells and see if the barrier that we have here, which is not large, is about 10 eV, or we can actually go lower, even lower. We have lower than 1 eV barrier for very short tubes. And we can compare static simulations with MD in this range, for instance, to see if the numbers agree. That would give us more confidence that those numbers are right, okay? And we did then 2 different simulations. One for a short tube on the left, and one for a very long tube. And these have exactly the same temperature and the same diameter. And you will be able to see that this one in the left will eventually collapse, right? So it must have a smaller barrier. And this one in the right will never collapse. Well, never is a very strong word, right? So as long as we ran the simulation, it did not collapse. I'm cheating a little bit because I'm running this in a movie that goes back to the initial picture. But you can trust me, Alexandre ran out of computer time trying to collapse this nanotube, and it never collapsed. So you can actually look at it, and you can see that it's not giving some indication that it will collapse, at least to me. But this one, you see that it will eventually collapse. So then we took this case and we performed calculations for many different temperatures, and we calculate for each temperature like 10 different realizations. We calculate the average collapse time, and we plot the log of the average collapse time as a function of 1/t, and that gives you a barrier, right? The slope of this gives you a barrier, which is 0.7 eV, which is very close to the barrier that we get from static minimization. So this is the final, okay, it already collapsed. So this is the final indication that the results from the static minimizations are right. So we can go back and try to interpret these experimental results in some way. So perhaps these very wide carbon nanotubes in a cylindrical shape they were just synthesized or created in a cylindrical shape and never had a chance to collapse. But why you have collapsed nanotubes at all? Well, there may be 2 reasons. First of all, perhaps during the synthesis process, they are already synthesized in a collapsed shape. But there's another possibility, which is they are collapsed because of some stress mechanisms, even during or after synthesis. Because one can actually calculate the force needed to collapse a carbon nanotube just by the derivative of this energy plot here, the potential energy plot. The derivative will give you the force. And actually, when you do the math, the forces are actually very small. So 4.5 nanometers is a very gentle push, for instance, using an AFM tip. This looks some sort of strange, right? I mean, the barriers are huge, but the forces are small. And this is okay, because the barriers are huge, because you have to apply a very small force, but for a very long distance to collapse the nanotube. So the work is very large, and the work is related to the barrier and not the force. So the conclusion of this is that the forces or the stress needed to collapse a carbon nanotube is small, and you can easily collapse. They are very soft. You can easily collapse them using an externally applied force, but using just temperature, just by thermal fluctuations, they will never collapse. Okay, so I think I'm almost running out of time. So again, as I promised you, I just flash some slides here about the other works we've been doing in our group and with collaborators in 2D materials. And then I will be happy to discuss them after the talk or during the week. In collaboration with Felipe Pinheiro at UFRJ, we studied the photonic spin Hall effect in bilayer graphene. Again, this is bilayer, twisted bilayer graphene. The photonic spin Hall effect, in a nutshell, is that if you shine some linearly polarized light, one can have a displacement of the beam, and actually you can have a left-handed and the right-handed circularly polarized lights and displaced. And this is an effect that we have shown that, well, starting from the real and imaginary part of the conductivity, one can calculate this shift, this effect, and you can see that this can be, again, this is very much dependent on the twisting angle, so it can be used as a way to detect the twisting angle in a carbon nanotube. This is a PRB last year. In collaborators with experimental people, mostly Aldo Jório at UFMG, we have been, this is a metrological work. We are trying to estimate the concentration of point defects and line defects, like crystallite size, in a disordered graphene samples, just by looking at the Raman spectrum for those systems. And we came up with analytical expressions that basically they look at the Raman, the D band and the G band of the Raman spectrum, and deconvolute those informations and obtain the concentrations of point defects and the crystallite size in graphene, a disordered graphene system. Relating to the talk of the previous talk, we also did tight binding parametrizations of black phosphorus, both monolayer and few layer and bulk. But we used sp3 parametrization, so this is it goes beyond the single orbital per atom parametrizations of Katznelson. This has been done by Marcos. This published last year as well. This parametrization is available for people who want to use them. I have studied also exploring different van der Waals DFT functionals to see how well they describe the interlayer properties of van der Waals heterostructures. This is in collaboration with Alexandre Leitão at the Federal University of Minas Gerais. These are some test calculations for molybdenum disulfide, and also we did graphite. So we exploring different versions of van der Waals functionals in DFT and to see which one is a good one to describe those systems. This is a similar thing that we did for graphene. In this case, we wanted to see how well it can describe this interlayer phonal modes. So this is layer breathing mode and the shear mode. These have been measured experimentally for different number of layers and also for graphite. And again, we also wanted to reproduce that with different functions, and actually to see which functional van der Waals DFT functional would reproduce those. And this is, I think, is the end. I'll thank you for your attention, and I'll be available here during the week, and I'll take some questions now. Thank you.